Hello, and welcome to Mirabilis Design's webinar series for 2025. I'm your host, Deepak Shankar, and today our first webinar is going to be in the automotive space, where we're going to discuss simulating automotive systems and architectures for power performance using VisualSim architecture. The automotive system is a fairly complex architecture, and it's fairly comprehensive as well. You have the network, which can be TSN CANs, your hardware gateways and ECUs, you have software, semiconductor, and of course, the big thing today is security, all kinds of cyber physical attacks and failures. A number of new applications are coming down the road, which needs a variety of support. For example, autonomous driving needs to be hardware software partitioning across multiple ECUs with sensors across the entire vehicle, to getting across the network for the data to arrive at the right ECU, scheduling the software tasks. So there's a lot of interactions. And each one of these products are created by a separate company or a separate organization. And how do you put all of these together? This is the way that you can really evaluate one particular architecture or do architecture trade-offs of an automotive system. If we take the automotive system, the baseline is the network. The network is the car. Now, within this network, you have a number of hardware components like ECUs, and they may have more details within them like CPUs and GPUs and AI engines and other components. Now, within the CPU GPUs, they have more semiconductor details like the processor, a HBM, or a multi-level chiplets, or a network on chip, things like that. And finally, the software. The software is what triggers the entire vehicle today. And these sequences get executed on not just one processor or one core, but across a multitude of ECUs and cores. So how do you really do an architecture trade-off with all of these different subsystems? And remember, all of this is required to form a complete automotive design environment. Now, when you consider a system of this kind, there's going to be a lot of trade-offs. And these trade-offs are not just coming out of one domain. They're coming out of hardware, network, software, power. So if you look at the statistics that are generated, you're going to notice that there is like the network stats. So, what is the latency across your gateway? Or how much is buffering has been in your switches? Or what is the maximum latency that it takes to go from channel 1 to channel 2? Or how many effective megabits per second are you getting? The next part is looking at the system. So in the system, you're saying how much a DMA operation, how much is the bus consuming, what is the processor minimum and maximum latency? And then you start looking at the software, in this case, the autonomous driving function, what's the latency? And you can actually see over time, most of them are within a small range of between 0.7 and 0.9 milliseconds, but then you see some spikes here that go almost 50% higher. So how do you ensure that you don't have these spikes? How do you ensure they're very consistent across the entire design? And another key aspect is power consumption. So today, as we transition to electric vehicles, the mileage is highly dependent on the amount of power that is being consumed. And of course, the last one is the semiconductor part. How do you, measure the statistics? How do you ensure you get maximum efficiency out of the statistics, especially across the caches, across the network on chip, across some of the chiplets and UCIe? How do you look at all of these aspects? Now, when I look at exploration, there is a network level exploration, which is I'm adding features to my TSN protocol, or I'm connecting to external interfaces. I've got the ECU hardware, which I need to size the processor. I need to select the right processor. I need to select the right amount of memory. I need to do the hardware software partitioning. So a variety of elements goes to forming the ECU hardware. Semiconductor, there's a lot of integration of analog and digital, like sensors and attenuators, and of course, the processing units. And today, there is no single processing mechanism. They're all complex SoCs with heterogeneous processing. Even FPGAs have heterogeneous compute. Now, how do you analyze this? And also the big question is, how do you transition to chiplets? How do you take advantage of chiplets? Then, of course, there's the power. The power is anything from generation to storage, it's the batteries, the distribution of power like a global clock power tree, the consumption management, and of course, what's the impact of thermal? So you can provide early information for cooling and planning of the mechanical structures. And finally, one of the key things that has to be done with all automotive systems is looking at security and also in terms of failures, cyber physical failures. So these could be intrusions or it can be loss of core. It can be a denial of service, or it can be that the number of coils in the generator reduces. And of course, there's the more traditional failures, which is there's a buffer overflow, or the network link cannot handle the required bandwidth, things like that, which are also in a sense a form of failure. Now, the first and foremost, when you look at the car, is really the communication network. It's really about the capacity planning and the topology. Now, in the past, we just had everything within the car, but today you have data centers, so you have partially at the edge, partially at the data center. You have communication with services on the road, with other vehicles, things like that, and those go through the gateways. Now, the gateway also handles the traffic between CAN buses to the TSN, and across the TSN network as well. And it's a question of how do you assign different ECUs, different sensors to these different networks. You have to also look at how many gateways do I need. A lot of those kind of questions. How many TSN switches and how many TSN networks do I need, for example. Similarly, when I look at these systems, based on the traffic, based on the workload, based on other aspects, I also have to do process selection for my different ECUs. I have to look at how many sensors. Could I get away with just 2 camera sensors running 4K recording, or do I need 6 camera sensors? How do I decide that? And then, of course, you have the chip design, but you also have the scheduler, which is your operating system, because you want to make your system as efficient as possible. And the scheduler design forms a large portion of it. Now, let's look at more detail on the hardware. Now that you saw the network, let's look at more detail on the hardware. So for example, this is a typical hardware system, can be at the chip level, or it can be at a board or a box level. So here we have AI engines, we have GPUs, we have HBMs, which are very popular and especially electric vehicles in the high end, and process subsystems. Now, one of the key things is when you look at this hardware architecture, is selecting the right processor. What is the clock speed? How many GPUs do I need? How many tensor units? Which processor should I be using? The second question will be, how do I create optimal mesh sizes? How many AI engines do I need based on my processing requirements or based on future processing requirements? How many ports should there be for the UCI, which is the chiplet to chiplet? What should be the buffer sizes? How many HBM slices do I need? Which is really about sizing the interconnect and the mesh. The next question, of course, comes up with the power. What is the thermal characteristics of my overall system? How many watts is the AI engine powering up, or how many watts can I reduce from my GPU when there's no processing happening? So looking at power management, looking at the distribution of power across the entire system to see if I can reduce my peak power. And of course, the key aspect of the design is really your workload. Workload comes in many forms. Workload can be the actual application. Workload can be traffic that's coming into each sensor. Workload can be overheads, things like diagnostics. Workloads can be the monitoring. There's a variety of things, and all of these run concurrently with the actual operation of the car. Alarms can also get there. Some of these have higher priority, some of them have lower priority. So those have to be considered as well. Now, when I look at this, the analysis I typically do are looking at round trip latency. What's the buffer usage? How much of throughput am I getting? What is the latency to go from here to the process subsystem versus the latency going to the memory? Is there a difference between the two? Now, when we look at the methodology that Mirabilis Design uses to enable this type of a system level exploration, you typically start off with an architecture block diagram. It can be of the network, can be of the ECU, can be of the semiconductor device. And once you have the architecture, you define two things. One is you take the basic components in the library, you drag and drop them and create a model. And then you apply different types of workloads against this particular model. Now, you take two things. One is your requirements, and you say, what are my different constraints? So, how much can the processor cache hit miss ratio be? Or, for each workload, how much a maximum latency can I have? How much should be the power consumed, the peak power? Answering all of these things. The other piece of it is, what are the elements am I going to modify? Am I going to modify the speed? Am I going to modify the cache size? Am I going to modify that, go from like, say, 1 gigabit per second on the TSN to a 10 gigabit per second? What am I going to be doing? Once I've defined all of these attributes, then I start doing the regression sweeps. The regression sweeps are really about determining what is the range for different aspects or different parts of my design. So, for example, we were talking about the buffer sizes or the connectivity between different ECUs to TSN networks, the assignment of software to TSN. So all of those can be regressions. And the way you evaluate them against the requirements is by generating the statistics. Can be latency, buffer occupancy, throughput, maximum power consumption, can be the hit miss ratio on a cache, can be a variety of statistics. Once you looked at all of these aspects and you iterate and you repeat by doing an optimization and trade-off, finally you come up and say, okay, this is my asset. This is what the system is going to be doing. So now I can reuse the same system either for testing, or I can reuse this for communication and collaboration with my partners, or I can use it for asset management for something that is more into the future. Now, how does VisualSim make all of this happen? VisualSim makes all of this happen really through the libraries. It has a large library of modeling components extending from processors to networks, to custom builders, to power systems. And using all of these, it's very easy and rapidly the user is able to assemble a model and run iterations and do the analysis. Now, one of the questions that always comes up, the system level modeling is very early in the design process. So how do I know it's all correct? The only way you really know is to create a baseline. Like in this case, we created a baseline where we compared the results from an existing system and compared it with the VisualSim model. So in this case, we looked at packet spacing and we looked at the ingress and egress side and compared the results. And we found that they were between 92 and 98% accuracy for a variety of traffic rates from 40 to 150 megahertz, and also for different types of reservations and for different types of scheduling algorithms. So it wasn't just one point that we're taking multitude of points. Not only was this baseline used to verify the model, but it was also used to scale the model. Because today's systems have a large number of nodes on the network and also a large number of network segments. So how do you scale them without having the simulation time run through significantly? Now, the VisualSim solution is really made up of three parts. One, it's completely graphical, and there you get to do all your trade-off of power, performance, failure, behavior, and thermal. The second part is the model of computation or the simulators. We have multiple simulators, unique one for each type of analysis. And finally, the integration with third-party solutions, third-party tools, or programming languages. Now, one of the things that happens is system level modeling is a new concept for many people. So rather than just handing off a software, we provide a variety of services to help you ramp up and integrate into your product design flow. And this ensures that you're productive very quickly, and also you have a long-term sustenance. Now, you learned a little bit about the basics of system level modeling, learned a little bit about what VisualSim has. Now, let's look at what we can provide to a particular designer. So we're going to take up, four aspects. We're going to look at the network. We're going to look at the hardware. We're looking at semiconductors, power, and finally failures and security. So when it comes to networks, the main goal is capacity planning. The capacity planning here is, you create your network by taking in either an ARXML or other kinds of standards that are available. Take those, assemble a model, determine where you want to integrate your sensors, your ECUs, your other subsystems, the connectivity to the data center, all of those. Then, of course, you describe all the other details like the routing table, your bandwidth, your clock speeds, all of those kind of things, your routing paths, all of those. And once you're done with that, you essentially created your network model. This model, the purpose of this model is not to determine what is the processor clock speed. The purpose of this model is to really understand the network. How is the network operating? What should be the scheduling algorithm? So one of the key things is what are the variations you want to do on the network? So for example, one of the key variations is really looking at what kind of scheduling algorithm, what kind of a switching mode. I'm using the TSN switch scheduler. What is the sense slope, idle slope? What is the class A and B percentage? Am I using store and forward or am I using flow through? All of those kind of questions. And those are the ones you need to vary. Of course, you have the TC10 timing as well for the power that also has to be taken into consideration. You can also have within the gateway, you can have different buffer sizes. You can have number of cycles for the actual software. So rather than modeling the details of software, modeling the details of the hardware, which are now abstracted, you can focus on saying, okay, this is the number of cycles it's going to take. And now, as a result of that, what happens to my throughput? Am I still getting the 150 megabits per second, or am I getting only like 30 megabits per second? Then, of course, you want to reuse things, standards like CAN/DB, to be able to import the traffic data. And then, of course, the other aspect of it, and a very important aspect of it, is the traffic. You need to be able to define traffic, not just for the sensors, but also when applications are running. Also, what is the bandwidth that's consumed on each of the networks? You may want to look at all of those aspects. And of course, if you look at the layers, you look at the TCP/IP stack, you'll have to look at, how many megabytes per second does it take to go through each layer of the stack? What is the buffer on each one of those? Answering questions like those as well. This is at the network communication level. So when you look at statistics, what you're really interested in is you're interested in trying out for particular latency or a particular application, what is my end-to-end latency? So here, for example, when I compared 124 nodes versus 5 nodes, you notice that the 124 nodes, the latency was at 6.8 milliseconds, while when I only had 5 nodes, it was 1.42. So we're looking at almost a 4x higher latency just because we had a much larger network, which means we had to go across multiple segments, multiple gateways, but also had to collide and compete with other traffic that's going across the network. The other aspect also is, looking at what kind of a scheduling algorithm do I use? How much of concurrent traffic is there on the network? So when we do these kind of settings, you can see, for example, the autonomous driving function has these special spikes over here. You can also see the traffic that's going between different channels. But here's the main thing. When you look at this table that's generated, you can see the buffer occupancy and the number rejected are very high for these networks, which also correlates to the traffic, the large traffic. And this is where you end up having a buffer overflow. And this is not just a performance bottleneck, but it's also a failure because you have loss of data, which means your card is not going to behave in the predicted manner. It's going to create collisions. It's going to create maybe a safety hazard, all of those kind of things. So you want to be able to analyze for different scenarios what happens to the operations within the car. Now that you looked at the network, let's deep dive into, say, the ECU and the sensor integration. So when you look at the ECU and sensor integration, first and foremost, there's going to be a large number of use cases. So there's going to be, like if you take in this case, the braking system, you have the sensors, you have the brake pedal and the proximity sensor that's triggering the brake action. Then you have the ECU itself, which has a processor for the brake ECU. Then you have the analysis, which is the time taken from the time the brake sensor or the brake pedal or the proximity sensor detects a potential hazard to the time that the brakes actually receive the trigger to say apply so much of pressure. Of course, across this whole system, how much was the power that was consumed? So when you take a network like this, you can see how the different components are connected across different networks and the gateways, where the locations the gateways are. And this here tells me, like this is the CAN bus and that's the gateway, which is transferring the messages between the different CAN buses. Now, when you look at a system like this, one of the first things you get to do is to translate it into a block diagram. So this is a format that VisualSim uses as a block diagram to take a conceptual idea into a more formal idea. So once you create this network and place all the ECUs, place all the sensors, define the gateways, then what you do is you describe the model using the VisualSim building blocks. So for example, that's the CAN bus, that's a sensor. These are the files that are used to define different attributes like the traffic, the routing table, things like that. And so the first and foremost you want to define is your setup. So these are all the setup tables. Then you want to define the CAN buses itself. Are we using CAN, CAN-FD, CAN-XL? Are we doing any power management within the CAN buses? Then what happens to the gateway? How do I connect these different segments through this gateway? How much are the ingress and egress buffers? What kind of bandwidth do I need to allocate for each data stream or traffic stream? Looking at all of those at the gateway level. Then I start looking at all the sensors and the ECUs and applying the same philosophy of how I connect them up. And then I look at run simulations where I start creating failures. What happens if one of the cores fails? Or what happens if there's reduced amount of power available? Or what happens if, say, there is a loss of data on the network, or creating an error packet, or sending a retry of a packet that actually finished correctly? What happens to my system? What is the behavior? How does that impact my failure, impact my hardware? So this is the definition of my hardware details. These are all the sensors. This is about what's in the brake ECU. And you can see this is the model of the hardware components within the brake ECU. And here you can see the statistics. So you can see what speed the car was going at, what was the latency on the processor, what the average power, what was the brake latency. Now, here's the thing that's interesting. Over time, you can see that the latency is actually going up, which is probably not a good sign because it means that there's some accumulated or some buffering that's happening in the design. So you really have to take a look at, is it happening at the network level? Is it happening at the chip level? Is it happening at the ECU level? So we can immediately correct it. This is where the different traffic models and workloads and use cases come into play. Now, now that we looked at the overall system, we added the ECUs and the sensors to the communication network. Now let's look at systems as a standalone component. So in this case, we have an infotainment system. In this case, the infotainment system is handling video cameras and it's outputting complete images within your screen, your 17-inch screen. It requires a combination of multi-core processors, GPUs, and display controllers. Now, this is a model that's created using VisualSim components. So each one of these entities constitute a component within VisualSim. And there's parameters for you on the top right for you to modify and try out some experiments. Now, when you do these experiments, you have these architecture trade-offs. So say you start off with 21 packets per second. What happens? You get 41 microseconds. But when you go to 210, which is 10 times, you get a 30x jump. But for example, when you go to 300 packets, you notice there's a buffer overflow, can handle it. So we find out that 250 packets per second is the system limit, cannot exceed beyond that because the FIFO has a buffer overflow. So using this, you can quickly determine where my bottlenecks are in the system. So now that you looked at the network communication, you looked at the ECUs, the sensors, the hardware in a standalone. Now let's look at the software side. So you can have AutoSAR or RTOS trade-offs in terms of, well, how do I set up my scheduling? What is how many cores do I need, or how many processors do I need to run this particular AutoSAR? How do I distribute the different applications across these different virtual operating systems? One of the key things when you run anything with software is to determine what is the level of abstraction you want to use. The reason is if you put in too much of detail, simulations will run extremely slow. Now, if you don't put enough details, the results will not be correct. So you have to have a trade-off between accuracy and the level of abstraction that you use. So typically what we do in VisualSim, in this case, we have a new application that we're adding, an autonomous driving application. And we have a bunch of ECUs that still have bandwidth available. So we look at, how do we distribute this autonomous driving without adding new ECUs? So that way we can keep the cost minimal, but still get the performance that we require. So these are what we call logical to physical mapping, and to run simulations to determine where the bottlenecks are, what is my latency, how much of throughput am I getting, evaluating all of those. Now, another aspect we want to look into is the semiconductor. And one of the key things in the automotive industry that's happening today is the transition to chiplets. Chiplets are subsystems that exist within the semiconductor device. So multiple chiplets can be connected together to form an application-specific ASIC. You can do this dynamically, which means that you can create these extremely fast. Within 3 months, you can take a bunch of chiplets that may come from multiple vendors, integrate them together, and be able to run a simulation, and then evaluate if this set combination works for this particular application or for this particular use case. So when we look at chiplets, let's take an example where we had a current SoC architecture with a single die. So you can see how they're all connected, how the CPUs are connected. We have the DRAMs for this set, we have a DRAMs here. For this set, we have DRAMs here. And of course, we have the task graph or the workload. Now, if we take this and create chiplets, you can see over here, we have 4 DRAMs, 4 CPU systems, but now we have 2 chiplets, which essentially means 2 dies that are created independently. But we also have issues. How do you connect them all together? Do you use 1 port or do we use 2 ports? Also, do we store all the data locally, or do we store data in the remote chiplet? So how do we distribute the memory capacity as well, such that we maximize the memory throughput and also keep the latency to a minimum? Again, we have the task graph, which describes the details of how the application is running and how the application is configured. In this particular case, when you do a comparison, what you notice, the monolithic die actually has a significantly lower latency, which is only goes to maximum about 3.2 or 320 nanoseconds. But here you can notice we're almost hitting 400 nanoseconds, and you also notice that the ranges are also significantly higher here. So there is a difference going from monolithic to multi-die. But one of the nice things that you notice is the increment with multi-die for power is very small. It's not very significant. So that's a big advantage because each of the dies is going to have less power consumed than when you have a single die. So cooling also helps in this particular case. So you benefit from a thermal impact as well. Of course, in this case, if you look at it, the latency to some extent is actually lower with the multi-chiplet. So you wonder, why is that the case? Because you got the UCIe overhead, which is pretty significant. What we found is that we have a better way to distribute the data across the different DRAMs. So by distributing the data across the different DRAMs and scheduling them slightly different, we could actually eliminate a lot of the bandwidth limitations and a lot of the performance limitations, and be able to get the latency lower. So this was one of the things that was key in this particular architecture, is that going over to multi-die does not mean you're going to increase your latency. In some cases, you actually have the ability to reduce the latency. Now, let's look at another aspect, because today there's a transition to high performance computing, especially with heterogeneous compute for both for edge processing and for data center. But today we're only going to focus on the edge processing. So we're going to take a DNN and or a convolution neural net. And we're looking at, if you take an operation in the ALU, there's like 4 memory access, 2 for operand, 1 for the partial sum, or the previous one, and 1 for storing the result. Now, if you store them all in an SRAM, which is on the chip, the power is going to be significantly lower than if you move them off chip. Now, the you can also look at how the other aspects, such as how much of your carbon footprint you're producing as a result of using these neural nets for making autonomous driving decisions, for example, or processing inside of my infotainment. So this is a challenge that's faced by a lot of the automotive vendors. Now, when you look at the hardware accelerators, typical hardware accelerators use some sort of an AI engine that has like an ALU plus some register, very small memory with a NOC that connects them all together, and an external DRAM. One of the things that's very important here is these things can, especially the DNNs, can consume significant amount of power. So it's very important that you keep the power low. And the only way to determine that is actually to run a simulation by taking this model of the DNN or CNN and run them against the model of the physical hardware. And you also want to see when there could be lower throughputs. For example, if I reduce the number of cores, or I increase the amount of memory on chip, or for example, I eliminate all the memory on chip and make everything go to DRAM, how does the latency change? Remember, the latency is a significant piece here if you want to achieve the performance requirements. So what you do is you create first a definition of what your CNN looks like. So you have your flow here and you convert that into the sizes. Then what you do is you create a model in VisualSim of the hardware, and you map each one of these to different resources within the hardware. Once you do that, you can run a variety of tests. So for example, here, I got 168 AI cores and 90% data is on the SRAM. So only for 10%, it has to go outside. You notice the power consumption is about 10.8 watts of power. The number of frames per second was about 0.414. Now we reduced the number of cores and still kept the 90%. And what we notice is the power reduced, obviously, but the frames per second also reduced to 0.29. Now, is 0.4 better or 0.29 better? It really depends. It really depends on what is your goals, what is the price point, what is your design requirements. That is why, if you remember upfront, talked about how you want to capture your design requirements and use it in the flow. Now, what happens if you keep 100% of data in the SRAM and you bump it up again to 168 cores? You'll notice the number of entries that are heading off across the XI bus to the DRAM drops significantly. Here's the thing, we were talking about 0.4 and 0.29. We're almost at 10 frames per second. Significant jump. But the interesting thing is the power didn't jump up so much. It's still at the 10.4. So we're actually not, even though we put this large number of cores, we did not actually increase the power by a significant amount. Matter of fact, it's slightly lower than the earlier scenario. And that is because when you use the VRAM, that has significantly more power relative to SRAM. We've been talking about power, but never really gone into details of what exactly is power in the automotive context. So in the automotive context, there's power which can be related to consumption, distribution, management, generating of test benches, and of course the thermal aspect. So when we look at power generation, it can be a solar panel, it can be a motor, it can be a variety of other things that you're generating power. One of the key things is storage. How are you storing this data? How many batteries or how many parallel cells do you have? And that would have a significant stay on your battery life cycle. What happens when you have surges and shocks? You want to capture that. The main thing you want to capture is your power consumption. How much is the power consumed by the overall system? Not just the semiconductors, not just the controller, but the entire, including the mechanical system. And you want to cover it not just for each device, but also for each application. So you know which application is consuming power. Of course, you also want to do power management to try to see if you can reduce it. We were looking at more of the hardware being modified, but we can also look at the management where we don't turn on the power as soon as the requirement happens. We delay it a little bit, or we as soon as it's done, we move down to a lower state. There are challenges there as well. For example, if you keep doing it too often, the transient time would end up being much greater and your performance would drop. When you do all of these, you want to see what happens to your heat and temperature because that determines your cooling strategy, which means that your cost-related cooling, your cost-related mechanical structure also changes. Of course, when you're doing these power type analysis, you may also want to provide sufficient data to the downstream development team so that they can use it to verify, debug, and also integrate it into their product flow. Now, if you take a model for the power integration, you can see here's my block diagram of the hardware. That's my behavior task flow. You can see a variety of statistics. So that shows me what's my instantaneous power. That's my heat plot. That's the number of frames per second. The temperature ranges. What's the average power? So you get a variety of statistics. And also, you get a table to tell you how much is the power that's going to consume in each of the states. So this is your input to the system. The output is not only the plots, but you can also get a waveform thing to see at what point, what state each of the devices were. So you can see, like, are there a number of devices being in the high active state versus the majority of them being this standby state. So you get, a different power profile. And of course, also the system Verilog and UPF files for using with the semiconductor teams to provide them the data to start doing the testing. Now, heat and temperature. So you can try to vary the time to reduce the power, reduce it by 1 degree. How much time does it take? So you can see, that the joules actually reduces here from about 5 to about 2.3, 2.7. And that is a significant, saving. Obviously, the ambient temperature was about 20 degrees centigrade. So that's why you're not seeing a significant difference. But there is a slight drop in the temperature as well. Now, the last aspect that we want to look at, which I know is not related to the network or hardware or power or software, but related to how the overall system behaves, which is failures and security. Now, VisualSim has these libraries that has a whole list of faults that can be injected directly into the system, and you can define different attributes for each one of those. So this is automatically provided to the model. And you can actually look at, no faults versus, when there's losses injected or incorrect addressing. You can see what the latencies are for each one of the paths. So it gives you an idea of how these types of faults will impact your overall system behavior. The other aspect is really the security aspect. So you have your system block diagram, you have your system model, say your TSN CAN with the ECUs. Now you want to see if I had some external intrusion, where there's a large number of devices that are doing a collective attack, a lot of connected devices doing a collective attack on your system. What happens? Where is the high resource usage? Is it at the gateways? Is it on the onboard units or the ECUs? where is the the high consumption. And why is that important? Because that starts determining what's your effective throughput. How does your response time change? So your high delay in processing requests in low throughput. So you want to analyze the system. So you have your existing block diagram fully validated. Then you apply these failures, you apply these security breaches, and see how the performance changes or how it impacts. So now what you're doing is you're trying to apply, say, the software on, say, the gateway, and then see what kind of an overhead it creates. How much does that reduce your communication bandwidth? How does that reduce, or I'm sorry, how does it increase your latency? And of course, you can look through to see what the normal operation is and what the under attack. You can see that we're going from like microseconds to like milliseconds, so significant latency. But you can also see at the same time that there's very high buffering that's occurring as a result of these operations happening within this particular design. So before we move on, I just want to give you a quick introduction to who Mirabilis Design is and what we do. So Mirabilis Design is an EDA software company based in Silicon Valley, and we really integrate all the teams together to be able to do one consolidated architecture exploration. We have a really, really strong management team that has been around the industry for a very long period of time. And we consistently win awards. Just in the last 4 years, we won about 6 awards across multiple conferences. VisualSim Architect is the modeling and simulation software, and it's got a large number of system-level modeling IPs. This is what allows users to very quickly assemble up systems. And over the years, we've been constantly adding newer and newer technologies. So you can use it for optimizing specification, or you can use it for collaboration with your suppliers, or to generate test scenarios, or to create failures. So we have grown over time to add more and more functionality that the users can benefit from. So in conclusion, one, it's a single platform for all companies involved in the automotive space to collaborate. You can do power, performance, and functional analysis. The system level IPs is what allows us to very quickly create any type of design in the automotive space. And the reason for doing system level modeling is to really eliminate all surprises and bottlenecks prior to development. And of course, we have a seamless integration with other simulators and code, so it allows you to use your legacy data or data that you might be more comfortable with, import those, or import your models into the VisualSim modeling environment. With this, thank you for attending our session, and hope you have a number of questions that we'll be happy to answer for you.